Hello, thank you for taking time off to view our presentation. Today, we have Yixing, Shuai Li, and myself, Chao Jian here to share with you our review of 3 papers regarding explainable AI planning. Yixing is pursuing a master's in AI full-time, while I am pursuing a master's in computer science full-time as well. Shuai Li is pursuing master's in computer science part-time. Here's the outline for our presentation. We'll be going through the motivation behind why we choose the topic, followed by the review of the 3 papers that we have selected. Subsequently, the evaluation metrics and the evaluation details for each paper. We will then end off with the conclusion. Here's why we choose this topic on explainable AI planning. For AI planning to be adopted widely, it has to be able to gain the user's trust, which means that it has to be able to explain their plan. In particular, the actions that they select in their plan. There are already legal framework in place for some parts of the world. For example, in EU, users have the right to explanation as stated in the EU General Data Protection Regulation in 2018. Moving on to review the papers, I'll be reviewing the first paper titled Towards Providing Explanations for AI Planner Decisions. It introduces a domain-independent methodology to provide explanation for the generated plan, which means it is suitable for any domains. It is capable of answering 3 questions that users may have upon reviewing the plan. Why did you do that? Why didn't you do something else that I would have done? And why is what you propose to do better than something else that I would have done? This is the algorithm for the methodology. As you can see, the input is an initial set of plans, in this case from the AI planner. Then we enter a loop to inspect the plan until the user is satisfied. First, the user will select a plan of interest, then it will choose an action to investigate, most likely an action that is questionable. The AI planner should be able to generate a list of alternative actions based on the constraint of that state. The user will then select an alternative action, most likely something that the user would have done. Then the AI planner will generate a new plan, and the effects of the user selected action can be reviewed by comparing the new plan with the previous plan. This new plan will be added to the set of initial plans to allow the user to continue to inspect this new plan in the next loop. This process will continue until the user is satisfied and confident that the plan generated by the AI planner is sound. There are 4 ways to generating a plan. First, by planning from the state after the user selected action. Second, by planning the whole plan again from the initial state with an additional constraint to enforce that the user selected action is performed. The third way is a variant of the second way by having one more constraint for the user selected action to be performed within a time window. This is to prevent the AI planner to perform the selected action as the last action and defeats the purpose of replanning, as the effects of the plan will not be comparable if the original action is not the last action performed. The last way is to generate both segments before and after the user selected action separately and join them together after that. There's a special scenario whereby the planner may undo the user selected action. This is done so if the AI planner revisits the same state that the original action was transiting to. Here, the author suggested to add an additional constraint to prevent the planner from doing so. However, the planner could still revert back to the original plan on the following state or some n number of states after that. I feel that this constraint is unnecessary, as it could mislead the user into thinking that his action actually made a difference to the plan. The implementation of the algorithm is good given that it is a paper on methodology and not implementation. Nevertheless, there are two possible challenges that I foresee. First, it is time-consuming for users to check through each action in a huge plan. Second, the user is unable to select two actions at once to suggest a cause and effect between actions. However, it could be overcome if the user walks through the plan and perform one more iteration again, which could be time-consuming if it is a huge plan. These challenges have the potential to limit the benefits of using AI Planner, which is to actually save time on planning. I believe more work is still required before this methodology is applicable beyond the research community.
Hi everyone, I am Yi Xing and I will be covering the second paper review and later on the evaluation of the three papers. Allow me now to share with you on our second paper, which is titled Towards Explainable AI Planning as a Service. As the name suggests, this paper proposes that explainable AI planning can be designed as a service which wraps around an existing planning system. The figure on the right shows the architecture for the framework. Based on some user questions, the service makes some modifications, such as imposing constraints to the model to create hypothetical models to output alternative plans. As the alternative plan is generated by the user's own trusted planner and model, this approach is expected to instill users' trust in the explanations provided. This can be an effective way of providing explanations and particularly important in safety-critical domains in which the user would not accept an explanation that is generated by a planner or model different from the ones they already use and whose performance they trust. The XAIP service is novel as a human-in-the-loop model refinement process. To allow the user to explore the set of hypothetical plans, the framework can generate a tree of contrastive explanations, and this allows the user to more precisely drill into the model behavior that they are interested in. The iterative process enables the extraction of the actions and temporal constraints or underlying assumptions which the user expects the model to take into consideration to continuously refine the model into one which matches the user's expectations. The service allows the user to see the original plan, ask a formal question from the set of contrastive questions, for example, why an action is not involved in a plan or why an action A rather than action B. So the user does this either by using a simple console interface or a set of forms for filling in the necessary details of the question. It also allows the user to give a question in natural language, then it derives a formal question in terms of states and actions and compiles the formal question into the planning language through an interpreter. The implemented interface also allows the users to select a formal question directly to avoid any ambiguity in the translation from natural language to formal representation. A limitation with the approach is the scope of explanation provided, as it only addresses contrastive questions and explanations. Users may not be trying to get contrastive explanations when asking why, but rather just trying to understand the conditions or requirements for various actions in the plan or the causal or temporal structure of the plan. In such cases, it would be more appropriate to highlight the causal structure in an abstracted version. The approach introduced a foundation for a contrastive explanation to enable the user to reason about the effect of the constraints that their question imposed and about the behavior of the model. The framework for the contrastive explanation in particular highlights the actions which were removed and added compared to the original plan, and displays the difference between the cost of the plans. The explanation is visualized on the GUI with the differences in the plan highlighted, and this can help the user to compare the plan with what the user was expecting. However, for larger and more complex plans, even a visual comparison can be challenging for the user to effectively compare and contrast plans. Some form of abstraction will be necessary, as the user might want to see only the important differences between two plans. So even though this approach is novel and seems promising to provide explainable AI planning as a service, to use back an existing planner to understand current plans, we see that there are still significant limitations for this approach to be used widely.
Hello, this is Li Shuai, and I will cover the details of third paper and the first part of evaluation. Okay, I will take the third paper, Encoding Compositionality in Classical Planning Solutions. So first of all, the motivations of this paper are related to the limitation of PDDL. PDDL makes it difficult to understand which literals are informing each action because they may have been introduced in previous steps. And if we want to evaluate the transferability, we have to validate compositionality within and between plans. So in this paper, they also proposed a novel encoding structure. String diagram is defined in the branch of mathematics called category theory. Here we list some properties of this theory. For example, each object has an identity, morphism, or mapping, and the composition operation all acts on morphisms. In this theory, there's also a symmetric Moidal category to support multiple objects in the domain and the codomain. As for the visualization in string diagram, we introduce the graphical syntax for illustration, maps, and their compositions. For example, here we attached a figure of conventional syntax and the string diagram syntax. In the case of string diagram syntax, the lines can be called strings, and these strings symbolize identity morphisms. So now we have introduced the structure of string diagram. Let's show some examples. In the famous Blackboard planning example, we use the string diagram to form the visualization of 4 steps. In each step, the string diagram can cover the details of actions and their relations. So we can have a very clear understanding of the actions and the context of this problem. Well, to conclude, I think in the string diagram, we can provide a causal explanation of a PDDL plan within the context of the domain and the problem with rigorous mathematics structure. And the structure permits reasoning about compositionality of plans, whether it be within the same solution or transformed solution. And it also allows user to sense the use of literals as the plan progresses. This can lead to insights about action dependencies. Okay, for evaluation, we proposed 3 metrics. Number 1, visibility, to check whether this approach is model agnostic and a need for menu remodeling. Number 2, transparency, to identify whether the approach allows user to understand the model in depth. Number 3, interaction, to measure whether this approach enables sufficient interaction with the users. For instance, the ability of providing human-friendly explanations.
The XAIP framework is model agnostic, and it allows users to meaningfully interact with any planner to elicit the explanations that users could want with the generated plan. Granted that it is a paper focusing on methodology, details on its implementation is rather brief, which means that more work is required before it is usable beyond the research community to show its feasibility. XAIP as a service is a wrapper around an existing planning system, so it is also agnostic about the domain model and the planner, and no manual remodeling is required. It is modular and can be used with all planners and domains that adhere to PDDL 2.1, but it is also the limitation that it can only work with PDDL 2.1. The proposed string diagram in the third paper is algorithm agnostic and is a model-based representation. This provides a causal explanation of a PDDL plan within the context of the domain and the problem with rigorous mathematical structure. However, the PDDL extensions supported are restricted, and there is a lack of implementation provided in the paper to show its usability. The XAIP framework approach enables the user to step through all actions and regenerate plans to observe the effect of the user-selected actions, so it is transparent about its result. However, the user is unaware that it is hard-coded, and that prevents the planner from undoing the action selected by the user if the user's action still results in going to the same state as the planner's selected action. The XAIP as a service approach outputs the action and cost of the original and alternative plans so that the user is able to compare the actions added or removed and the corresponding differences in costs among the alternatives to elucidate how the two plans achieve or fail to achieve the goals of the problem with respect to specific actions in the domain. This enables the user to gain confidence on the quality of the plan found by the planner. The service is envisaged to be used iteratively for explainable planning, whereby the user is able to use the framework to iterate the process by asking further questions to continuously refine the revised domain model. The iterative model refinement based on the user's questions will help the users to better understand the model constraints and assumptions and refine it to the user's expectations accordingly. However, it is unable to provide explanations based on causal or temporal abstraction, such as why was this sequence of actions taken at this time. The string diagram in the third paper permits reasoning about compositionality of plans, whether it be within the same solution or a transferred solution. In addition, the representation provides a diagrammatic syntax that identifies rectangles as actions and curvy lines or strings as literals. The placement of the rectangles and strings relay a temporal progression, read from top to bottom, which allows the user to sense the use of literals as the plan progresses. This can lead to insights about action dependencies. However, the string diagram approach is unable to encode relationships between positive and negative versions of the same literal, which will pose some limitations for the user to fully understand the model. Our third and final evaluation metric is on interaction. The implementation in XAIP framework is primitive and does not consider the scale of plans in terms of complexity and volume. There are also other issues like, for example, requiring the user to translate their questions into selecting the correct generate plan implementation to use. For XAIP as a service, interaction with the user is enabled through a console interface as well as a graphical user interface. The user can make use of the GUI to examine the alternative plan's differences in actions and costs to the original plan to assist in his reasoning of the suitability and accuracy of the models. However, this may not be viable for larger and more complex plans. In terms of inputs, the service framework is modular to enable different ways for the user to communicate a question to the AI system, including asking questions in natural language, or even possibly to be extended to work with speech recognition input modules. While the authors managed to address the issue of translating questions from the first paper by allowing questions in natural language, most challenges still remain to be solved before it can be employed reliably for more users. In the third paper, it is very easy to present interactions, such as highlighting the strings of a particular literal in order to witness its path through the plan, or sliding rectangles along strings to view alternative plans. However, the visualization may not be able to scale effectively without abstraction, which was not discussed in the paper.
This is Chao Jian here again, and I will be summarizing the evaluation done earlier and conclude the presentation. In summary, for usability, the paper of XAIP as a service and encoding compositionality are more user-friendly compared to XAIP framework. This is because the focus of the XAIP framework focuses more on the methodology instead of implementation, whereas the authors from the other two papers place more consideration on usability. On transparency, only the XAIP framework paper is considered not fully transparent due to its hidden constraint to prevent undoing of user-selected action. For the last metric, interaction, again, the XAIP framework do not perform as well as the others due to its focus on simply presenting the methodology. The interaction is limited to just proof of concept of the methodology, unlike the other two papers which have designed their work with users in mind. In conclusion, XAIP have been progressing steadily. First, starting with defining a roadmap for Explainable AI Planner, which provides 6 questions that the user may ask. This paper is not covered here, followed by providing a model-agnostic framework in line with the roadmap, capable of answering 3 out of the 6 questions, and subsequently the implementation of the framework as a wrapper to make it usable beyond the research community. More recently, there are also research trying new ways of presenting the AI plan through abstracting the states and actions. These progress so far are promising to reveal the black box of AI Planner, and in turn is gaining potential for more widespread adoption by gaining users' trust and meeting legal regulations. Thank you for completing watching our presentation. Have a nice day.